Hi, I'm Lucien Hardy. I work at Perimeter Institute. Today I'm going to be discussing quantum theory, quantum gravity, and indefinite causal structure. Okay, so put simply, the problem of quantum gravity is to find a theory, probably a new theory, which reduces in appropriate limits to Einstein's theory of general relativity on the one hand, and to quantum theory on the other hand. So I should probably unpack that statement a little bit. So general relativity is Einstein's theory of gravity. He developed it in the years leading up to 2015, and it followed on from his theory of special relativity. Um, and in order to develop that theory, really, it was in some ways perhaps the most spectacular feat, academic, intellectual feat by any one individual in the history of human thought. He had to really think differently about the way space and time worked. Not only were space and time unified, as in special relativity, but space and time could actually bend. So it's a very beautiful, very striking theory, and it is in its own way quite conceptually novel, quite strange. So that's general relativity on the one hand, Einstein's theory of gravity, and then on the other hand we have quantum theory. So quantum theory was developed by a bunch of different people. Planck is usually regarded as the person who got the ball rolling with his theory of black body radiation. And then there were many contributions, including actually by Einstein, leading up to contributions by Heisenberg and Schrödinger, who, in some sense, were the people who really wrote down the quantum theory in its modern form for the first time. In fact, we're coming up now to the 100 years of quantum theory. So it was 1925 that Heisenberg wrote his paper, so almost 100 years ago. And quantum theory is a very strange theory. It's conceptually very odd. It really puts it puts measurements at the center. It puts the observer at the center of what's happening. So it's a very strange theory. Perhaps the strangest thing in quantum theory is the phenomena of quantum interference. So in quantum theory, you can imagine a particle can get from A to B. It can go by one path or by another path. And what happens there is that there is a sense in which it goes along both paths at the same time. Quantum theory, you get this weird thing called quantum superposition, and it leads to an experimental phenomena called quantum interference. And from that, you infer that a particle is taking one or two paths at the same time. So you've got these two theories, quantum theory and general relativity. And the problem of quantum gravity is to find a new theory that limits to those two theories in appropriate limits. So what I mean by that is you might imagine that general relativity, in certain experiments, you would expect to see Einstein's theory of general relativity hold up. And in other kinds of experiments, you'd expect to see quantum theory hold up. And then there would be experiments where neither of them would work precisely, perhaps, but you'd get a new domain where you're really doing a quantum gravity experiment. And and the problem is that these two different theories are conceptually very different. They make very different conceptual assumptions about the way the world works, and so it's hard. It's hard to find a theory that that reduces in appropriate limits those two different theories. And people have been working on it now for a long time, uh, uh, and, um, and that's the problem I'm fascinated by.
So I've always been curious about this question. Now, as far as I understand, we have uh, strong quantum theories of many other forces, including like electromagnetism, for example, the weak force, the strong force. Why is why is gravity the odd one out?
I think the best answer to that is that gravity is about the very fabric of space-time. Those other theories postulate particles that live on top of space-time, but take, or those other forces, you imagine fields that live on top of space-time, but take space-time to be a fixed structure. Whereas general relativity, space-time itself is something that's dynamical. Um, Now you can cheat a little bit and imagine small perturbations in space-time, uh, and you can treat that as if you have some fixed background space-time structure with little perturbations on top of it, and then it behaves a lot like the theories you mentioned. But if you get into something which doesn't fit that perturbative framework, if you have strong perturbations, then it starts to break down. So so there's something very different about quantum theory compared with these other theories. That's my opinion. You'll get people have different opinions on this, but that's my feeling. And and there's something even a bit stranger, um, which is how to explain this. In general relativity, what happens is that your equations are invariant under coordinate transformations. So, what do I mean by that? You lay down some coordinate system. We used a coordinate system, so you have x, y, and z, and also in general relativity you also have t, you have x, y, z, and t. Um, and So we used that kind of idea. But in general relativity, you have a structure that is prior to space and time. It's called a manifold, and you put space and time on top of that structure, and you do that by specifying something called a metric. It gives this manifold, which is a prior structure, it gives it spatial temporal structure. And but that manifold, before you put anything on top of it, you have to put some coordinates down, okay, to describe that you've got this point or that point or another point, and um, and then you write down some equations, and your equations don't really care how you put those coordinates down. You have the equations have the same form regardless, and this ends up meaning that those coordinates you put down have no intrinsic meaning in themselves. You only get meaning in general relativity by looking at the values of physical quantities in reference to one another. So it's a kind of relational thing that physical quantities, uh, fields that live on this background structure, this manifold, uh, take values relative to one another, and that's where you get the physical meaning. The coordinate system you place down in the first place has no meaning in itself, and this was something that Einstein struggled with. It was one of the reasons for him, taking his time to get to his field equations. It took him a while because he struggled with this problem that the background structure, that the coordinates were not really intrinsic. They didn't have real meaning in themselves. It was only these relative values of coordinate of physical quantities that mattered. So so that's something quite different as well.
I see. Um, and so you've taken a fascinating approach to this issue. Uh, in 2001, you formulated all of quantum theory, starting from five uh, axioms. I believe you call this an operational approach because of the fact that uh, it only considers these physical quantities which you can measure. And it doesn't, I guess, postulate about what exists in the world. Um, so, in layman's terms, what are these axioms and how do they tie into the problem of unifying quantum theory with general relativity?
Okay, so so there's a few things I'd like to address there. I'd like to talk about what I mean by operationalism. Um, I'd like to tell you what the axioms are, and then I should also mention that at the time I did this work, I wasn't interested, especially in the problem of quantum gravity. That's an interest that came along for me later, especially when I moved from Oxford to the Perimeter Institute. Um, so, operationalism. Operationalism is like you say, it's looking just at quantities we observe. Well, it's a bit more than that. When we do experiments, we choose different settings and then we make observations. So there's the things we do, and then there's the observations we make. And operationalism concerns um, describing the world at that very basic level in terms of what we do and what we see, and just attempting to make predictions in that context without positing necessarily some deeper level of reality. It's You can either regard operationalism as as something fundamental, you might say, well, there isn't any reality beyond what we do and what we see. Or you might say operationalism is a methodology. It's a way of extracting the essential physics without getting misled by some preconceived notions about an underlying reality. So, an example of the success of operationalism was, again, back to Einstein when he set up the theory of special relativity. And there was, at the time, there was this preconceived notion of an um, absolute time. So, there's an absolute time, there's an absolute now, and an absolute time across the whole universe. And so, it made sense before Einstein to talk about what is happening on Mars right now. Uh, and so Einstein set up his ideas using sort of rods, measuring rods, and clocks, and he defined his terms very carefully in an operational way. And he was able to see that this idea of absolute simultaneity um, was had no place in physics. He got rid of that idea. So operationalism can be very successful, very useful from a methodological point of view. Um, and for me personally, it's that methodological uh, use that I find compelling. Um, I still personally think there is some underlying reality, and it's the job of physics to get to that. But we may have to take a circuitous route to get there. So, so that's what operationalism is. The axioms. Um, the idea was to try and think of some axioms or postulates that were somehow compelling. So, because you can write down, you'll find axioms for quantum theory in the standard textbooks, but they're very ad hoc, they're very mathematical. They're not the kind of things that are immediately compelling. Uh, and a historical analogy would be if you look at Kepler's laws. So Kepler had these laws for the motion of the planets. So equal planets wipe out equal area in equal times, and uh, planets move in ellipses, and so on. So he had these laws, and they were pretty good from a predictive point of view. You could predict the motions of the planets, but they didn't seem to have an explanatory value. So, so something was missing, and then Newton came along, and with his laws of mechanics, his three laws of mechanics, and his law of universal gravitation, showed how to actually do something that seemed more like it was explanatory. So he showed how you could predict these elliptical orbits and all these laws of Kepler. And actually, he did a bit more because he also showed that you could predict things like hyperbolic motion. So if you have some comet that comes from deep outside our solar system, then rather than traveling on an ellipse around the sun, it's coming in from essentially from infinity, and it travels on a hyperbolic path, and that wasn't predicted by Kepler. So Newton's laws went beyond that, and then also the planets perturb each other, and using Newton's laws, you could predict those perturbations with quite a lot of success for most of the planets. Although interestingly, not Mercury. To understand Mercury, we had to go to Einstein and general relativity that came along later. So so there's a good reason for there's a good reason for trying to come up with axioms or postulates which are somehow more explanatory and less ad hoc. So that was the goal.